December 25th, 2021, Christmas morning. While most of the world was unwrapping gifts and sitting around breakfast tables, a rocket lifted off from a launch pad in French Guiana, carrying something that had taken 40 years, 20,000 scientists, and $10 billion to build. It was a telescope, but calling it a telescope is like calling the ocean a puddle. This machine, folded like origami inside the nose of an Ariane 5 rocket, was designed to do something no instrument in human history had ever done. It was designed to see time, to look so far into the darkness of space that the images it captured would show us the universe not as it is today, but as it was 13.6 billion years ago, closer to the moment of creation than anything we had ever glimpsed. But here's what makes this story extraordinary. It almost never happened. There was a moment back in 1995 when one stubborn, gray-haired man sat in a conference room surrounded by colleagues who told him his idea was reckless, career-ending, a waste of the world's most expensive telescope on a patch of sky where absolutely nothing existed. He ignored them, and what happened next rewrote everything humanity thought it knew about the universe. This is the story of how we built an eye to see God. To understand what the James Webb Space Telescope is, you first have to understand the man who made it necessary. His name was Bob Williams. In 1995, he was the director of the Space Telescope Science Institute, the body that oversaw how and where the Hubble telescope pointed its lens. A veteran scientist, a careful man, a man who had spent decades learning that the universe rewards patience above almost everything else. That year, Williams made a decision that his colleagues thought was professionally suicidal. He pointed the Hubble telescope at nothing. Not almost nothing. Not a faint corner of the sky with a few dim stars. Nothing. A patch of black space, so apparently empty that the strongest argument against the decision was simply, there is nothing there. You will photograph darkness and call it research. The NASA team was furious. They brought numbers, projections, political arguments. The US government's budget for NASA was already under constant threat from skeptical senators. The Hubble telescope had cost billions. To tie it up for 10 days, 10 consecutive days, pointing at empty space, producing nothing, would hand their opponents in Washington exactly the ammunition they needed to cut funding. Bob Williams listened to all of it. He heard every argument, and then he did it anyway. Here is why. Williams understood something about light that most people never stop to consider. Light has a speed 300,000 kilometers per second. It is the fastest thing in the universe. And yet, even at that speed, the distances of space are so enormous that light takes time to travel. Years.
Centuries. Billions of years. Which means every time you look at something in the night sky, you are not seeing the present. You are seeing the past. The light reaching your eyes left its source long before you were born, before humans existed, before Earth itself existed. A patch of sky that looks empty to the naked eye might be hiding something extraordinary. Galaxies so ancient, so far away, that their light has been traveling toward us since the universe was young. Only now arriving, faint and stretched, barely detectable. Williams believed that if you gave Hubble enough time, if you kept the lens open long enough, it would catch that ancient light. He was right. The Hubble telescope spent 10 days staring at that blank patch. The aperture stayed open for 100 hours. It captured 342 individual images, each taking 25 to 45 minutes. Scientists spent the next 17 days assembling those images like a jigsaw puzzle, applying scientific color to reveal wavelengths the human eye cannot process. What they found stunned the world. In that single patch of apparently empty sky, a region you could cover with a grain of sand held at arm's length, there were more than 3,000 galaxies. 3,000 entire galaxies, each containing hundreds of billions of stars, each potentially harboring planets and oceans and stories we cannot begin to imagine. The image was called the Hubble Deep Field, and it changed everything. The Hubble Deep Field image did something dangerous. It answered one enormous question and immediately raised another. If a 10-day exposure of an empty patch of sky could reveal 3,000 galaxies, how many more were hiding in the darkness, beyond even Hubble's reach? And more importantly, could we look even further back? Could we build a telescope powerful enough to photograph the very first galaxies? The galaxies that formed in the first few 100 million years after the Big Bang? Because here is what the Hubble Deep Field images were telling scientists. The most distant galaxies Hubble could capture, the faint, reddish smears at the edge of its vision, were 12 billion years old. The universe itself is 13.789 billion years old. That meant humanity was standing 1.8 billion years away from seeing the actual beginning. 1.8 billion years. A gap that sounds impossibly large, but by cosmic standards is agonizingly close. Scientists began debating two paths: upgrade Hubble, push it beyond deep space into what they were calling ultra-deep space, or build something entirely new, something bigger, more powerful, more advanced than anything ever constructed. They chose both. Hubble was upgraded and pointed at another blank patch of sky, this time keeping its lens open for 11.3 days across months of observations from September 2003 to January 2004. The resulting image, the Hubble Ultra Deep Field, contained more than 10,000 galaxies, some of them 13 billion years old. It was the deepest image of the universe ever captured, but it wasn't deep enough. And it was painfully, frustratingly slow. To go further, to see those last 1.8 billion years, scientists needed a machine that could do what Hubble could not. And to understand why Hubble had limits, why it couldn't simply be pushed further, you need to understand something remarkable about light itself. This is where the story gets strange. Consider this. Right now, in the room where you're sitting, there is light you cannot see. Your television remote control sends a signal to your screen. You press the button, the TV responds, but no color travels between them. No visible beam crosses the room. Something invisible is doing the work. Your microwave heats your food using waves you cannot detect. Radio stations broadcast into the air around you constantly. You walk through their transmissions every second of your life without sensing them. These are not mystical forces. They are light, the same fundamental phenomenon as the light from a candle or a star, but at wavelengths beyond what the human eye evolved to detect. Below the red end of the visible spectrum lies infrared light. Longer wavelengths, lower energy. Invisible to us, but absolutely real. Absolutely detectable with the right instrument. Now here is why this matters for astronomy. When a galaxy or a star is very far away from us, not just millions but billions of light years away, something happens to its light during the long journey through expanding space. The universe itself is stretching, and as it stretches, the wavelengths of light stretch with it. Visible light gets pulled into longer and longer wavelengths. By the time it reaches us, the light from the most ancient galaxies has been stretched so far that it has shifted entirely out of the visible spectrum into infrared. This is called redshift, and it means that the oldest light in the universe, the light from the very first galaxies, is invisible to any telescope that cannot see infrared. Hubble's primary instruments are not infrared instruments. Hubble sees the universe roughly the way our eyes do. It can capture some infrared with added cameras, and those additions dramatically expanded what it could see. Scientists showed side-by-side images
where thousands of additional stars appeared the moment you switched to infrared. But Hubble was not designed for this. It was not optimized for it. To see the beginning of the universe, you needed a telescope built from the ground up as an infrared instrument. That telescope had a name. And here is where the story takes a turn that involves a man most people outside of NASA have never heard of. The telescope's official name is the Next Generation Space Telescope, but NASA named it after James Webb, the administrator who ran the agency through the 1960s during the Apollo program, the man who presided over the moonshots. He had retired 9 months before Neil Armstrong stepped onto the lunar surface on July 20th, 1969. But his name would now carry further than any astronaut had ever traveled into the infrared darkness at the edge of time. Building the James Webb Space Telescope required solving problems that had no solutions when the project began. Start with the mirrors. James Webb's primary mirror spans 21 feet and 4 inches, nearly 3 times the width of Hubble's mirror. But you cannot launch a rigid 21-foot mirror on a rocket. Rockets have fairings nose cones that are only so wide. The mirror had to fold, 18 separate hexagonal segments, each one a mirror in itself, that would launch folded like the petals of a flower and then unfurl in space, aligning themselves with a precision measured in nanometers. Each of those 18 segments had to work perfectly. Every single one. If even one failed to deploy correctly, the entire mission would fail, and there would be no repair mission. James Webb orbits 1.5 million kilometers from Earth, 4 times further than the Moon, far beyond the reach of any crewed spacecraft. But the mirrors themselves presented a deeper problem. To capture infrared light, the cold, ancient, low-energy light from 13-billion-year-old galaxies, the telescope's mirrors had to be extraordinarily cold. If anything near the mirrors is even slightly warm, that warmth emits its own infrared radiation, contaminating the signal.
The mirrors had to operate at minus 223 degrees Celsius. That is 50 degrees above absolute zero, the coldest achievable temperature in a working spacecraft. Ordinary glass cannot survive those temperatures. Ordinary metals warp, crack, become brittle. Scientists and geologists spent years searching for the right material. They found it in beryllium, a rare, lightweight metal mined from deposits in the American Southwest. Beryllium remained stable even in the savage cold of deep space. It was mined, powdered, pressed into hexagonal forms, and polished to a smoothness that defies ordinary description. Then came the gold. Each mirror was coated with a microscopically thin layer of gold. Not because of its value, but because gold reflects infrared light better than any other material. Ordinary glass absorbs infrared. Gold bounces it directly where you want it to go. The layer was so thinner than a human hair that all 18 mirrors combined required only enough gold to make 4 small rings. 4 rings worth of gold, spread across a mirror system the size of a small house. But even perfect gold mirrors at minus 223 degrees would be useless if the sun's heat reached them. So engineers designed 5 sun shields, each one the size of a tennis court, to be positioned between the mirrors and the sun at all times. These shields are made of a material called capton, a carbon-based compound only 1/1000th of an inch thick, strong enough to survive decades in space, effective enough to reduce the sun's heat from something that would boil water to something colder than the dark side of Pluto. 5 layers, each separated by a gap. Heat that penetrates the first layer is trapped and dissipated before reaching the second. Layer by layer, a wall of cold is maintained around the mirrors. The challenge was folding all of this, the shields, the mirrors, the entire assembly small enough to fit inside a rocket, then engineering a system that would unfold it perfectly
automatically 1.5 million kilometers from the nearest human hand. There were 344 single-point failure mechanisms, 344 individual steps that had to work without error. Any one of them failing meant the telescope would be lost forever. When the Ariane 5 rocket launched on Christmas Day 2021 and the telescope began unfolding in the darkness, scientists at Mission Control tracked each of those 344 steps in silence, one by one, checking, waiting, breathing. Every single one worked. Here is something that the headline coverage of James Webb almost never explains, and it reframes everything about what this telescope actually is. When James Webb sends us an image, it is not a photograph in any ordinary sense. The telescope's cameras, primarily the near-infrared camera, or NIRCam, and the mid-infrared instrument, or MIRI, do not see colors the way your eyes do. They detect wavelengths of light that are entirely invisible to human perception. The stunning images you see, the nebulae blazing in gold and crimson, the galaxies shimmering in blue and purple, those colors are translations. Scientists assign visible colors to infrared wavelengths to make the data comprehensible to human eyes. But here's the extraordinary part. Those color assignments are not arbitrary. They encode information. The redness of a galaxy in a James Webb image is not decoration. It is data telling you how far away that galaxy is, how fast it is receding, how old its light is. Every pixel in a James Webb image is a measurement. Every shade is a scientific statement. NIRCam's lens, by the way, is not made of glass. Glass absorbs infrared light. The lens is made of lithium fluoride, a salt compound, because salt reflects infrared back through the system rather than absorbing it.
A salt lens on a gold mirror inside a tennis court-sized cold chamber orbiting 1.5 million kilometers from Earth, photographing light that has been traveling since before our solar system existed. The resolution of James Webb's images is 20 times higher than Hubble's equivalent. Every pixel contains more information, and in space science, a single pixel can be the subject of an entire PhD dissertation because embedded in the curve of a distant galaxy, in the spectral signature of a dim star, is information about how matter behaved 1 billion years after the Big Bang. The Hubble telescope has already become the reference for more than 10,000 published scientific papers. James Webb is expected to multiply that. And then, in July 2022, James Webb released its first images. And the scientific community went very, very quiet. The first image was of a galaxy cluster called SMACS 0723. It sits 4.6 billion light-years from Earth. But the image wasn't really about SMACS 0723. Scattered throughout the image, partially hidden, partially revealed, were galaxies behind the cluster galaxies so massive and dense that their gravity bent the light passing near them, distorting the images of more distant galaxies into arcs and curves. This phenomenon is called gravitational lensing, and it was first predicted by Einstein. James Webb was seeing it with a clarity no instrument had ever achieved. And buried in the image, once scientists began measuring wavelengths, were two galaxies that dated to 13 billion years ago. One to 13 billion, another to 13.1 billion, sitting there in a corner of a picture of a relatively nearby galaxy cluster, as if they had been waiting. James Webb produced this image in 12.5 hours. Hubble had taken 4 months to image the same region at a fraction of the resolution. The second image was the Southern Ring Nebula, a cloud of gas and dust 2,500 light-years away in our own galaxy. At its center, a dying star. For thousands of years, that star has been shedding rings of gas outward in every direction, like ripples from a stone dropped in water. We were watching a star die and understanding that our own sun will end the same way.
in approximately 5 billion years, its outer layers expanding into space, its core collapsing into a white dwarf that will glow for billions of years before finally going dark. The third image was a portion of the Carina Nebula, a stellar nursery 7,500 light-years away. Nebulae are the birthplaces of stars, vast clouds of gas and dust that gravity slowly compresses until the pressure at the core ignites nuclear fusion and a star is born. The cliff-like edge of the nebula visible in the image is so tall that light takes 7 years to travel from its top to its bottom. The full nebula, at the speed of light, would take 16 years to cross. In James Webb's infrared image of the Carina Nebula, stars that were completely invisible in Hubble's visible light image appear in their thousands infant stars, newly formed, still wrapped in cocoons of gas, stars being born in real time. If you consider 7,500 years ago to be real time, and then there was the fourth image, the one that stopped scientists mid-sentence. The fourth image was called Stephan's Quintet. It was constructed from over 1,000 individual images taken by James Webb, assembled into a single composite, the most complex image the telescope had produced to date.
5 galaxies, visible together in the same frame, located between 40 million and 300 million light-years from Earth, 4 of them locked in a gravitational dance, slowly merging, colliding in a process so gradual that it will take hundreds of millions of years to complete. The image contains not just 5 galaxies, but hundreds of others in the background, an entire population of galaxies that were simply there in the same patch of sky waiting to be seen. But it was what the mid-infrared camera revealed that made scientists go silent. Switch from the near-infrared view to the mid-infrared view of the same image, and a black hole appears. Not in the background, not lurking at the edge of the frame, right there in one of the quintet's galaxies. A supermassive black hole so enormous that 25 million stars the size of our sun could fit inside it. Invisible in visible light, invisible in near-infrared, but glowing in mid-infrared, because the material spiraling into it superheated gas, and shredded matter radiates at exactly those wavelengths. James Webb had photographed the unseeable. Now step back and consider what this all means. The universe is 13.789 billion years old. The light that reaches us from the most distant objects James Webb can observe left its source when the universe was only a few hundred million years old, when the first stars were just beginning to ignite, when the first galaxies were taking shape from clouds of hydrogen and helium that the Big Bang had scattered in all directions. James Webb is not just a more powerful telescope, it is a time machine. Every image it sends is a window into the past, a past so deep that the galaxies it photographs may no longer exist in the forms we see them. They may have collided with others, been torn apart by gravity, been consumed by the black holes at their centers. What we are seeing is their light, the record of their existence, finally arriving after a journey of billions of years. And here is the thing about that light. It has been traveling through space this whole time, since before the Earth formed, since before the sun ignited, since before the Milky Way took the shape we recognize. All of that ancient light has been moving through the dark at 300,000 kilometers per second for billions of years, and it has arrived in the 21st century at exactly the right moment, at exactly the right place, to fall upon 18 gold-coated beryllium mirrors, be focused by a secondary mirror, pass through a salt lens, and be recorded by sensors built by human hands. The odds of that convergence are almost too large to contemplate. Bob Williams pointed Hubble at nothing in 1995 and found 3,000 galaxies. James Webb pointed its mirror at the same kind of darkness and found the edge of time.
Both moments trace back to the same stubborn, patient, magnificent refusal to accept that what we cannot see does not exist. James Webb launched with fuel for 10 years. Its trajectory was precise enough that it may last 20 to 40. The 5 images released in July 2022 were not science. They were a demonstration, a proof of concept, a way of saying the machine works. All 344 steps deployed correctly, all 18 mirrors aligned. The gold is cold enough. The sun shields are holding. We are ready. The actual science, the systematic, disciplined, decades-long work of imaging the early universe, measuring the atmospheres of distant planets, searching for the chemical signatures of life that has barely begun.
Consider this. The Hubble telescope has been operating since 1990, 35 years. In that time, it has been the reference for more than 10,000 published research papers. Its images have been studied, pixel by pixel, by researchers on every continent. Its data has shaped the careers of entire generations of scientists. James Webb is 20 times more powerful. It sees wavelengths Hubble cannot. It operates in a colder, darker, more stable part of space. And it has potentially 40 years of fuel. 40 years of images we cannot yet imagine, of light that has been traveling since the first moments after the Big Bang, arriving one frame at a time in the cameras of a telescope built by 20,000 people over 4 decades of collective human effort. We are standing at the beginning of something. And yet, here is the thought that should make you pause. The one that scientists don't always say out loud. We are still looking at the past. Every image James Webb sends shows us what was, not what is. The galaxies in those images may be gone. The dying star in the Southern Ring Nebula may have already completed its death. The infant stars in the Carina Nebula may be ancient by now, with their own planetary systems, their own histories. We will never know what they look like today. The light hasn't reached us yet. Somewhere in the darkness, at this very moment, ancient light is still traveling toward us. Light from events we cannot yet see. Light from the very first moments after the Big Bang, carrying information we haven't imagined questions to ask. In 40 years, James Webb will help us ask them. In a way, it already has. Somewhere in a field in New Mexico, a grain of sand held at arm's length covers a patch of sky that contains 10,000 galaxies. And somewhere in those galaxies, in the cold and the dark, light is moving, patient, indifferent, ancient, toward a mirror made of beryllium and gold, still waiting to show us what we do not yet know we are looking for.